this video, we're going to determine which regular n-gons are constructible using Euclidean tools. Remember what Euclidean tools means. You can use a compass and you can use a straight edge. I'm just going to use this for the straight edge. I'm not going to use this protractor to get specific angle degrees. You can't do that. If you do, you're not using Euclidean tools, and we don't call it constructible. So we can only use this compass and a straight edge. Okay, so here is the statement from Gauss. A regular n-gon is constructible with Euclidean tools, meaning with a compass and a straight edge, if and only if, if and only if the number n is equal to this product. Notice it's a power of 2 to the k power. K can be anything 0 or greater, and so can r. Here's r. So it could be 2 to the 0, which would be a 1. So that power of 2 is not really required. It'd be 2 to the 0. 2 to the 1 would be a 2. 2 squared is 4, or 8, 16, 32, 64, ... Some power of 2 times these F1, F2 through FR. Now, since R can be 0, if R is a 0, none of those exist. In that case, n would just be a power of 2. So another way of saying that would be n is a power of 2, or it's a power of 2 times distinct Fermat prime numbers that we learned about in the earlier video, the previous video. Notice F1 through FR, they have to be distinct. They can't repeat. Okay, so in particular, this theorem means that every 2 to the k gon is constructible. And we've already constructed a square, which is a 2 squared gon, or a 4 gon. We constructed a regular 4 gon, which is a square. And then for these numbers in particular, we're going to do a little example here. For 3 through 25, determine which n-gons are constructible. Which of them can be written like a power of 2 times distinct Fermat primes. Well, since we're only going up to 25, the only Fermat primes we need to worry about, F0, which remember is a 3, F1 is a 5, F2 is a 17. We don't need to worry about anything else because we're only going up to 25. Now remember, we also have a 2 to the k here. So we can use these numbers, and we can also use any power of 2. I must have lost my light there. See if I can get it back. Okay. All right, well, actually, I already wrote about for you. These are the ones that are constructible, and we will show it by what is 3? 3 is 2 to the 0, which is 1. No, you don't need a power of 2 at all, times capital F0, which was 3. So that's just, I'll just write it down as 3, because 3 is F0. 4 is, let's see, it's 2 squared. We don't even need to multiply by any of the Fermat primes, F0 or F1 or F2. It's just the power of 2, 2 squared. And while I'm thinking about that, I'll go ahead and get 8, which is 2 to the 3rd. 16 is 2 to the 4th, and that's all the powers of 2. And then we move on to 5. Well, 5 is just F1, so I'm just going to write 5. So it'd be 2 to the 0 times capital F1. The number 6 is 2 times 3. The power of 2 is just 2 to the 1. And then times 3. Oops, sorry about that. Wrong one. 2 times 3. The power of 2 is just 2 to the 1 times F0, which is 3. We did 8. 10 is just 2 times 5. 2 is the power of 2. 5 is capital F1. What's 12? It's 2 squared times 3. It's a power of 2 times F0. 15 is 3 times 5. No power of 2, but it's got F0 times F1, two distinct Fermat primes. 17 is just 17, that's F2. 18 would be 2 times 3 squared. That's the power of 2, and then that's F0. Well, let's see, 3 squared. Actually, it has to be distinct. 2 times 3 squared should not work. So I'm going to take the number 18 out of this list because they need to be distinct primes, Fermat primes. So yes, let's remove 18 from that list. And then 20 is 2 squared, that's 4, times 5. So we have a power of 2 times F1. And then the last one that is constructible is going from 3 to 25. The last one is 24. That's 2 to the third times 3. That's 8 times 3, a power of 2 times F0. So let's see, what does that leave us as not constructible? Would be 7, a 7-gon, regular 7-gon is not constructible. 9, 11, 13, 14, I need to include 18 in there, 19, 22, 23, 25. So none of these, a regular 7-gon, a regular 9-gon, all the way up to a regular 25-gon, those are not constructible. Okay, a corollary to this by Baran, mathematician. An angle of measure 60 degrees cannot be trisected using Euclidean tools. That is the compass and straight edge. What does that mean to trisect it? It means to take a 60-degree angle, which is constructible, take that 60-degree angle and then break it up into 20-degree segments, 3 20-degree angles. And that's impossible using Euclidean tools. And how are we going to prove that? Well, in a brainstorm, first, is a 60-degree angle itself constructible? And it says explain. Well, of course. We've done it in a previous video. We constructed an equilateral triangle, which means you have 3 60-degree angles. We know we can construct a 60-degree angle. If a 60-degree angle, I should have put angle there. If a 60-degree angle can be trisected, then that means that what is constructible? A third of 60 degrees. A 20-degree angle is constructible. Let's see if that makes any sense here. And the answer is no. The answer is going to be no. I mean, we already know it. It cannot be trisected, 60-degree angle. So we cannot create a 20-degree angle. Let's prove it. To the contrary, so we're going to do a proof by contradiction. Assume an angle of measure 60 degrees can be trisected. And we'll reach a contradiction which would prove then that assumption is false. Okay, if it can be trisected, that means that a 20-degree angle is constructible. Therefore, or so, a regular polygon with 18 sides is also constructible. How can I say that? Well, notice, if you break up if you have an regular 18-sided polygon, each angle from the center of it to the endpoints of each side would be 18 degrees. 18 times 20 gives you 360 degrees. So you'd be making a bunch of 20-degree angles. Let's see if we can construct an 18-sided regular polygon. What is the prime factorization of 18? We already did it up there. The prime factorization of 18 is 2 times 3 squared. Well, remember we came up with that originally. We made a mistake up here. 18 is 2 times 3 squared. That means it is not constructible because f0 equals 3. Remember the Fermat primes? f0 is a 3. Is a factor twice. It's squared. Is a factor twice. And that theorem, that contradicts Gauss's theorem, which says they need to be distinct Fermat prime numbers. So since this one showed up twice, we know that we've reached a contradiction. Therefore, when we said to the contrary, assume an angle of measure 60 degrees can be trisected, that is false. So that's a proof of this corollary by Veron.